Let's discuss in a few exercises, about properties of logarithms. First, we have these four basic properties of logarithms. The first property says that the log in base a of 1 is equal to 0. So basically, what the first property let us know is that regardless of the base, when the argument of the logarithm expression is 1, that logarithm expression is equal to 0. So, for example, the logarithm in base 3 of 1 would be 0, the common logarithm of 1 would be 0, or the natural logarithm of 1 would be 0. The second property we have say that the log in base a of a is equal to 1. So basically, in this property, when the base of the logarithm expression and the argument of the logarithm expression are the same, that expression is equal to 1. So we have that the logarithm in base 5 of 5 will be 1, the common logarithm of 10 will be 1, or the natural logarithm of e will be equal to 1, based on this property. My next property is that that a to the power of the logarithm in base a of m is equal to m. So basically here we have an exponential expression with base a, and the exponent of that exponential expression is a logarithm expression base a also. So in this case, we have that the result or the value of the expression will be equal to the argument of the logarithm expression. So we're going to explain this side involving these properties, so I will later just explain more about it. And finally, we have that the log in base a of a to the r is equal to r. So you have a logarithm expression with base 8, and the argument of that logarithm expression is an exponential expression base a. So in this case, the result of the expression, or the value of the expression, will be equal to the exponent uh, of the argument of that logarithm expression. I will use this also in some examples later. So let's then solve this exercise that is given over here. Let's say use properties of logarithms to find the exact value of each expression. We'll use a calculator. Well, they say log in base 3 of 3 to the power of 71. So of course, if we look at the properties we have on the top, we see how, using this property, we can solve this expression. We can find the value of this expression. The value of this expression is 71 because the logarithm in base 3 of 3 to the power of 71, that will be 71 based on the property log in base a of a to the r is equal to r. Later we have this other case, let's say 2 to the power of the logarithm in base 2 of 7. Well, based on this property here, we know that this is going to be equal to 7. Why? Because when you have a to the power of the logarithm in base a of m, that is equal to m, the argument of the logarithm expression. So we have here how the base of the exponential expression and the base of the logarithm expression that is exponent of that exponential expression are equal. So the result is just the argument of the logarithm expression. Now here we have to use one property that about exponents, or the rule of exponents, to say that x to the n over x to the n is equals x to the power of n minus n. So that means that when you have a quotient of two exponential expressions with the same base, you can subtract exponents. Or you have an exponential expression where the exponent is a difference between two expressions, you can rewrite that as a quotient. And that's exactly what we're going to do in this case, because we have 3 to the power of the logarithm base 3 of 5 minus logarithm base 3 of 4. So I can express this as a quotient. So you can say this is 3 to the power of the logarithm in base 3 of 5 over 3 to the power of the logarithm in base 3 of 4. Now, using this same property over here, so the same property that we have used in number 17, we can say that 3 to the power of the logarithm in base 3 of 5 is 5, and 3 to the power of the logarithm in base 3 of 4 is equal to 4. So the result in this case is 5 over 4. Here we have 3 of now other important properties of logarithms, like the logarithm of a product equals the sum of the logarithms. So when you have the logarithm in base A of a product of two factors, you can rewrite this as the sum of the logarithms of those factors, giving the same base, of course. The log of a quotient equals the difference of the logs. So when you have the logarithm in base A of a quotient, you can rewrite this as a difference between the logarithm of the numerator minus the logarithm of the denominator. And you have that the log of the power equals the product of the power and the log. So when you have the logarithm in base A of m to the r, this exponent r can be written as a factor. So it will be r times the logarithm in base A of m. So you break it, you basically, rewrite the exponent as a factor, or you can also write a factor as an exponent if needed. Let's then solve some exercise using those problems. First, we have this case. They say suppose that ln of 2 is equals 8 and ln of 3 is equals b. So use the properties of logarithms to write each logarithm in terms of m. So when I see natural logarithm of 6, I immediately realize that 6 is the product of 2 times 3. So I can say ln of 2 times 3. Now, based on the previous properties of logarithm, the logarithm of a product is the sum of the logarithms. So you can say this is ln of 2 plus ln of 3. If we know that ln of 2 is 8 and ln of 3 is b, we get that this ln of 6 is equal to a plus b. My next case is ln of 2 over 3. Well, we have the quotient, so we can rewrite this as a difference. So we can see this is ln of 2 minus ln of 3. If ln of 2 is 8 and ln of 2 is b, we get here a minus b. So this was a very easy exercise to apply the product and the quotient property. Let's solve now this exercise. They say write each expression as the sum of difference of logarithms express the powers of factors. So we have log in base 5 of 25x. So we have a product. So we can rewrite this as log in base 5 of 25 plus the log in base 5 of x. Now I realize that 25 is 5 squared. So we say log in base 5 of 5 squared plus log in base 5 of x. Now log in base 5 of 5 squared, we write this exponent as a factor. We say that this is 2 log in base 5 of 5 plus the log in base 5 of x. Now we know that log in base a of a is equal 1, so log in base 5 of 5 is equal to 1. So we get 2 plus the log in base 5 of x. And this is how we write the expression log in base 5 of 35x as the sum of difference of logarithms expressing the powers as factors. Now we have this other case. Log in base 3 of x over 9. So we're going to use now the property that they write this quotient as a difference of logarithms. So we say this is log in base 3 of x minus the log in base 3 of 9. 9 is 3 squared, So we say this is the log in base 3 of x minus the log in base 3 of 3 squared. We will be rewriting now this power as a factor. So we say this is the log in base 3 of x minus 2 log in base 3 of 3. Of course, here this is 1. So we get that this is log in base 3 of x minus 2. And here we got the result. With this same order or question, write each expression as a difference of values and express box of factors. Then we can go over these other two exercises. We have natural logarithm of x times the square root of 1 plus x squared with x greater than 0. X greater than 0 basically gives us the domain of this expression. So we don't have to worry about this x greater than 0. We don't have to worry about this x greater than 3 because this is the domain of this other second expression. So what we're going to do is just apply the property of logarithms. As I have a plot, I can rewrite this as a sum of logarithms. So I can say that ln of x times the square root of 1 plus x squared is equals to ln of x plus the ln of the square root of 1 plus x squared. Now, every time that you find a radical, you must rewrite this radical as a rational exponent. So remember, you know that the n root of x is x to the power of 1, right? So the square root can be written as, say, ln of x plus ln of 1 plus x squared to the power of 1. Now, when I have my radical as a rational exponent, I can bring this exponent now as a factor. And I can say this is ln of x plus 1 over 2 ln of 1 plus x squared. And we can just rewrite that. So don't try to apply any property to this expression 1 plus x squared because the logarithm of a polynomial just stay like that. My next case is this, log in base 2 of x to the third over x minus 3. So we have a quotient. We're going to break this as a difference of logarithms. This is log in base 2 of x to the third minus the log in base 2 of x minus 3. Now, of course, we bring this power as a factor, so you can say 3 log in base 2 of x minus the log in base 2 of x minus 3. And we can just say there's no confirmation. Now, exactly as we are in these four exercises expanding the logarithm expressions or writing a single logarithm expression into a multiple logarithm expression, we can just do the opposite process. That is when we combine logarithm expressions. So when we go from multiple logarithm expressions to a single logarithm expression. So in this case, they say write each expression as a single logarithm. And we have 3 logarithms in base a of u plus 4 logarithms in base 5 of v. So what are we doing? First, we're going to be writing these factors as exponents. So I want to say that this is log in base 5 of u to the third plus log in base 5 of v to the fourth. Now we have the sum of logarithms. So we're going to rewrite this as a single logarithm where the argument is the product of these two arguments, v to the third and v to the fourth. So this is the log in base 5 of v to the third, v to the fourth. So it was really easy. It's just basically to apply the two properties, the power as a factor and the product property. Let's see this other case. Log in base fourth of x squared minus 1 minus 5 log in base fourth of x plus 1. So we have a difference. So we rewrite this as a quotient of the logarithm but before, and we just write these factors as an exponent, as a power. So we say that this is the log in base 4 of x squared minus 1 minus the log in base 4 of x plus 1 to the fifth. So this would be now writing this difference as a quotient, log in base 4 of x squared minus 1 over x plus 1 to the fifth. We're going to now factor x squared minus 1, so we have the log in base 4 of x plus 1, x minus 1 over x plus 1 to the fifth. Now, I will simplify this x plus 1 with 1 of the x plus 1 below, and we get this the logarithm in base 4 of x minus 1 over x plus 1 to the fourth. And there we go. Over single logarithm expression. Now, there is another important property, and I will give you examples about this property in this short video because we have a video where we use this property to solve equations. So if we have that there is an equality between two expressions, we can apply logarithms to both sides. So we can get that if m is equal to n, then the logarithm base a of n is equal to the logarithm base a of n. But also, if we have an equality between two logarithmic expressions, we can say that the arguments of those expressions are equal. See, this property in these two different forms is a very important property to solve both logarithmic equations and exponential equations. Finally, I want to go over the change of base formula. Change of base formula say that the log in base a of m can be written as log in base b of m over log in base b of a. So you have the logarithm base a of m. You can change the base from a to b, and you can express this logarithm base a of m as the logarithm in base b of the argument over the logarithm in base b of the original base a, of the base a of the original expression here. Now, most of the calculators include the functions natural logarithm and common logarithm. So usually when we want to evaluate using changes to a formula, a logarithm other than 10 or e, other than logarithm base 10, logarithm base e, so other than common logarithm or natural logarithm, we usually convert that into using changes to a formula into a quotient of two common logarithms or two natural logarithms. So if I have the logarithm in base a of m, I can either say that this logarithm base a of m is the logarithm of m over the logarithm of a, so common logarithm of m over common logarithm of a. Remember that common logarithm is the logarithm base 10. Or we can say that log in base a of m is equal to the natural logarithm of m over the natural logarithm of a. Remember the natural logarithm is logarithm base e. So for example, when I have this exercise where they say use the changes to base formula and calculator to only the logarithm, round to three decimal places. They say log in base 3 of 21. I will just verify this as a quotient of two either common logarithm expressions or natural logarithm expressions. I would prefer to use natural logarithms. So usually, when I have to pick between common logarithm and natural logarithm, I usually use the natural logarithm. So we say this is a log of 21 over n of 3. But it's going to be the same. You say log of 21 over log of 3. Sorry, log of 3. So you have to give you exactly the same answer. And the answer in this case, when you already with your calculator, n of 21 over n of 3 is 2.77. Well, my dear student, thank you so much for your attention. I hope this video is useful for you, that you just enjoy the video and learn from it, and see you in the future.